In this lecture, we start a discussion of constraint problems, and in particular, we focus on problems with equality constraints first. All right, so the problem with equality constraints in the general form is given here. We want to minimize the objective function f of x subject to the equality constraints h of x is equal to 0. So here, even though we write it as a single equality constraint, in fact, it consists of m equations here. So because, as we can see here, the objective function maps a point in Rn into a real number, whereas h of x in the constraints is given by m functions. So essentially, this is a function that takes an argument in Rn and maps it into an m-dimensional vector, so which is given by the following. So it is h1 of x, then h2 of x, and so on, hm of x. All right, so for every point in Rn, we will have the corresponding m-dimensional vector given by this here, so by h of x. The assumption usually is m is less than n, because we are talking about the equality constraints here. If we had more equations than we have variables, this would result in an overdetermined system, which would often be infeasible. We want to make sure that we have a non-trivial feasible region here for this problem. Now, what is a feasible point? Of course, it's a point that satisfies all the constraints here, a point for which h of x is equal to 0, which means that we have h1 of x is equal to 0, h2 of x is 0, and hm of x is 0. So all of hi's for I between 1 and m are equal to 0. Okay? So this set that is given by the set of all feasible points, which are the set of all the points where h of x is equal to 0, is the feasible set of our problem, right? So next we discuss some notations that we have not previously used in this course so far. Now we are dealing with a function h of x, which is from Rn to Rm. So we need to express the first order derivative for such a function somehow. So, and in this case, you have a function that takes values in m-dimensional space, right? To express all first order derivatives, we actually need a matrix like this. So in this matrix, each row corresponds to the first order derivatives of one of the functions hi with respect to all the variables, right? We have the gradient of h1 of x transposed in the first row, the gradient of h2 transposed in the second row, and so on for all the rows in this matrix. And this matrix is called the Jacobian of the function h at the point x. There is also a concept of a regular point for constraint problems. The regular points will be the points for which we will have the optimality conditions actually. If the point is not regular, then the optimality conditions that we'll discuss will not apply to such problems. Okay? So what is a regular point for a problem with equality constraints? We will call a point x star a regular point, and we are talking about a feasible point here, right? So we will call a feasible point x star a regular point if the Jacobian has the full rank, so which means that these m vectors here are linearly independent. So the gradients of h1 through hm at x star are linearly independent. Next, we discuss the first order necessary conditions for problems with equality constraints. We'll skip the details of how we derive these conditions. Instead, we'll actually state the Lagrange Theorem, and I will try to explain how you can actually understand these conditions intuitively and how we can easily remember them, okay? So the Lagrange Theorem states that if x star is a regular point and the local minimizer or maximizer of the problem of optimizing f of x subject to the equality constraints, where all the functions involved here are continuously differentiable, then there exists the set of lambdas given by lambda 1 through lambda m such that this combination here, so the gradient of f of x star plus the sum for I between 1 and m of lambda i's times the gradients of h i's is equal to 0. Let's see what exactly this means, all right? So we have the problem of minimizing f of x subject to h1 of x is equal to 0, h2 of x is equal to 0, and so on. hm of x is 0. We assume that x star is a regular point and also a local minimizer for this problem. We can try to reduce our problem to an unconstrained minimization problem by moving the constraints into the objective with a certain penalty. Let me denote the new objective that includes these penalties by L of x lambda. So lambda will be the penalty coefficients, and the objective will be as follows. So first, we have the original objective function f of x, and then we add the functions in the constraints with the corresponding penalty multipliers lambda 1 through lambda m. So we'll have lambda 1 times h1 of x plus lambda 2 times h2 of x, and so on, lambda m times hm of x. Okay, so we see that if either a multiplier or the corresponding hi of x is equal to 0, then this term lambda I times hi of x doesn't change the objective, right? So, and let's say if all of these were equal to 0, then we would just have f of x. So in particular, if we had a feasible point for which hi's of x are all equal to 0, then L of x lambda will be the same as the objective function that we have for our problem. All right. So, but now let's just treat L of x lambda as a function that we want to minimize. So if we wanted to minimize this function here, then we would apply the first order necessary condition, right? In addition to the original variable x, we also have lambdas here. So the multipliers, we can treat them as variables. So as a result, we have m additional variables, lambda 1 through lambda m, and the total number of variables now will be n x's and m lambdas, so the total number of variables is n plus m. When we apply the first order necessary conditions to this function here as for an unconstrained optimization problem, first we take the derivatives with respect to x's, okay? We know that the gradient of L x lambda with respect to x's must be equal to 0, and the same thing actually with respect to lambdas as well, right? So if we take the partial derivatives with respect to lambdas, this gradient should also be equal to 0. So this vector of length n plus m, if we combine both of these, must be a 0 vector, right? Now let's see what this means for the part of the vector that corresponds to the partial derivatives with respect to xi's. So when we take the derivatives with respect to x, we'll have the gradient of f of x, right? Then plus lambda 1 times the gradient of h1 of x, and so on, plus lambda m times the gradient of hm of x. All right, so and this must be equal to 0. So now when I take the derivatives with respect to lambdas, this is a constant with respect to lambdas, and then if I take the partial derivative with respect to lambda 1, I have h1 of x, and then everything else doesn't depend on lambda 1, so it's just h1 of x is equal to 0, right? So if I take the partial derivative with respect to lambda 2, it will be h2 of x equals 0, and so on. If I just take the derivatives with respect to lambdas, I will obtain h of x is 0. So which is exactly the feasibility for our problem. So as a result, we have the gradient of f in x plus the sum for i's between 1 and m of lambda i's times the gradient of hi of x is 0, and then h in x is 0. Okay, so this is our condition here, which is exactly the condition that we have in the Lagrange theorem. Okay, so obviously this is not a rigorous proof of any sort, so this is just something that hopefully will provide intuition for these conditions and will help you to remember what the conditions are about. The lambda multipliers that we are using and the function L of x lambda that we consider here, they actually have the name. So the lambda i's are called the Lagrange multipliers, and this function L of x lambda is called the Lagrangian of the problem. So L of x lambda is the Lagrangian. L of x lambda is a function of n plus m variables, as we mentioned. So when we apply the unconstrained first-order necessary condition to the function of the Lagrangian, this is what we obtain. So this is exactly the conditions in the Lagrange theorem. So here we have just a system with m plus n equations and m plus n unknowns. Okay. An important assumption here is that x star is a regular point. If x star is not a regular point, it can still be a local minimizer but not satisfy this Lagrange condition. All right, we can apply this necessary condition only under the assumption that the point is regular. All right, so when we solve a constrained problem, first we need to check whether all the feasible points are regular or not. If a point is not regular, then we need to treat it separately from the regular points. For example, consider the following problem. So we want to minimize x2 minus x1, a linear function, subject to a single constraint, which is given by x1 squared minus x2 cubed is 0. So this is just a two-dimensional problem, so we can actually illustrate it geometrically. So in this case, the equality constraint is the same as x2 is given by x1 to the power 2/3, and we can actually draw the plot for this function. So this is our x1, this is x2. x2 equal to x1 to the power 2/3 is something like this, roughly. All right, so now let's try to see what happens if we apply the Lagrange theorem. Before we apply the Lagrange theorem, we need to check whether all the feasible points are regular or not. H consists of just h1 of x, so there is only one constraint, and the gradient of h of x is given by 2 times x1 and then minus 3 times x2 squared. So in this case, the Jacobian coincides with the gradient, right? So, but in general, the regularity condition tells us that the Jacobian must be the full rank matrix. Okay, so if you look at the gradient here, what are the conditions when this will be a full rank matrix? The only way it is not full rank is when this vector is equal to 0, in which case the rank will be 0, otherwise the rank will be equal to 1, right? So, and the only way this vector is a 0 vector is when both x1 and x2 are zeros. So we are talking about this point here, the origin, right? So this is the only point which is not regular, so the only feasible point which is not regular. Therefore, we need to treat this point differently. If you apply the Lagrange condition, the fact that this point is not regular tells us that even if this point doesn't satisfy the conditions in Lagrange theorem, it can still be a candidate for a minimizer. Okay, so we need to consider it as a candidate. So now let's apply the Lagrange theorem. So we have the gradient of f, which is given by -1, 1. So this is the gradient of f, and then plus lambda. So in this case, there is only one constraint, so there is only one lambda, right? So lambda times 2x1 minus 3x2 squared is 0. We need to find the points that satisfy this condition. So let's write these conditions again here. So we'll have the first equation will be 2 times lambda times x1 is 1. Then the second equation will be 1 minus 3 lambda times x2 squared is 0, so which is the same as 3 times lambda times x2 squared is 1. And the third and the final equation will be the equation that we have in the constraint here. So it will be x1 squared minus x2 cubed is 0. All right, so we need to solve this system in order to find the points that satisfy the Lagrange conditions. So we can express x1 and x2 through lambda from the first and the second equations respectively. So from the first equation we'll have x1 is 1 over 2 lambda. So from the second equation we'll have x2 is plus minus square root over 1 over 3 lambda. All right, and finally we plug in x1 and x2 expressed through lambda in the third equation, so we'll have 1 over 4 lambda squared minus, we'll have two cases, right? So the first case will be plus square root of 1 over 3 lambda, and the second one will be minus square root of 1 over 3 lambda. So let's consider plus first. So we'll have 1 over 3 lambda to the power 3/2. So this is 0. So we have 3 lambda to the power 3 over 2 equal to 4 lambda squared. All right. So we take the square of both parts, and then we'll have 27 lambda cubed is the same as 16 lambda to the power 4. So as a result, we'll have lambda, so we can divide by lambda because lambda is not equal to 0, obviously. We'll have lambda is given by 27/16. So this was for the first case where we used the plus here. Okay, so now we need to consider the second case where we use the minus. So for the second case, we'll have the following equation. So we'll have case 2, 1 over 4 lambda squared plus 1 over 3 lambda to the power 3/2 is 0, right? So if you look at the details here, we have 3 lambda to the power 3/2 here, so which means that lambda must be positive, right? Obviously, for positive lambda, this will be positive, this will be positive, and their sum cannot be equal to 0. In this case, we don't have the solution. So the only point that satisfies the Lagrange theorem here is lambda equal to 27/6, and then x1 is given by 1 over 2 lambda, which is 1 over 2 times 27/16, which is the same as 8/27. And then for x2, we have square root of 1 over 3 lambda. All right, so we have square root of 1 over 3 times 27/16, which is 4 divided by 9. All right, so we have the point 8/27, 4/9. The corresponding Lagrange multiplier is 27/16. This point will be somewhere here. In fact, if we draw the isocost line here, so isocost line will be x2 minus x1 is given by a certain cost. So let's do the isocost line that passes through the origin. So it will be just the x1 equal to x2 line. And this point here will be the point where the isocost line is tangent to the line representing the feasible region. We can see that if we move the isocost line, so if we move it up, we don't have any feasible points around this point that we found from the Lagrange condition. So as we can see from the graphical illustration, this is a local maximizer point. All right, so this is a local max.
It's just like really the opposite of what we're going for here.
Let's go back to the point of the origin, so 0, 0. This point, we saw that it was not a regular point, therefore we need to treat it separately. We need to consider it as a candidate for a local minimizer, even though it doesn't satisfy the equations of the Lagrange theorem. If we look at this point and we just consider the geometrical illustration, then we can see that in fact this point is a local minimizer, because if I look at the isocost line, and if I consider some small neighborhood of this point, then if I move my isocost line down, we'll see that within this neighborhood we don't have a point of intersection with the feasible region. So therefore, this point is the best in this neighborhood, so it is a local minimizer. So we see that in this case, because the point is not regular, even though it doesn't satisfy the first order necessary condition, it is still a local minimizer. All right, so the assumption that the point is regular is very important here, so that's the message. However, in probably most cases that we'll consider, all points in the feasible region will in fact be regular, and then we'll have to look for a minimizer among only the points that satisfy the first order necessary conditions. The first order necessary condition consists of a system of m plus n variables and m plus n equations, and in general this system is quite challenging to solve. And also, we still have the same deal as we had with the unconstrained minimization problems. Even if we solve the system, this is just a stationary point, so this is only a candidate point for a local minimizer, but it can be a saddle point or a local maximizer, so it can still be a useless point for us. So, but then again, we'll discuss some sufficient conditions for minimizers that we can apply to see if this point is indeed a local minimizer or not. But again, in general, in some cases, these conditions will also be inconclusive, so in general, it's difficult to verify whether the stationary point that we find is a local minimizer or not.